people on Zoom and fewer in.
They have to go between buildings. Otherwise.
Well, no, there are a lot of people here that are from the outside.
Okay.
From greater Gainesville area. The lady with the dog is, for example.
Okay. Very good.
Probably everybody who's in a heavy jacket is either from a house.
Yeah.
Because you can walk through the buildings. You get anywhere in apartments, but there's houses, so there's really, these two are. Yeah, so there are a number of people.
Good. Well, good. Of course. You have a little dog.
I have a medium-sized dog. Which has been a great, so she's an extremely friendly dog. So as a result, I've gotten to know all sorts of people, and there are a number of people that know her name. This is John Axe, by the way. The last time astronomy was taught here in ILR, he did it.
Oh.
And I think he must have had some background. Don't know him very well because he's also but doesn't have a dog, so I don't know him. Statistician. Other places. Data processor.
Probably lights down on the front would be good, just because makes the picture stand out better.
What's that?
You're asking about the lights, right?
Yeah.
I mean, less light in the front is good to make sure the pictures stand out well.
Okay. Maybe that's the second one, the one just about tone darkness.
Yeah, sure. But,
And if you want to change it, let us know.
What's it loaded?
Yeah, well, yeah, when the time comes. The second one. First one is
yeah. Turn the lights on the front, back up.
yeah, whatever works.
Fair enough.
Oh, I can control them if you need. If you need anything adjusted, but you can control it too.
I know you do that. I tried it once before. I couldn't do it.
I think that thing there affects all the lights.
But to go down and get back, I can't control that.
Good afternoon. Welcome. Okay, remember, if you have cell phones, if you would please silence them, I'd appreciate that. Zoomers, please stay muted. But if you have questions at the questions and answers, put them in the chat, and we will ask the speaker. Jane Brockman is going to introduce our speaker for today.
Okay, well, thank you. Welcome. Thank you for people who came in from the cold, so to speak. So our speaker today is Adam Ginsburg. He is an associate professor in the Department of Astronomy at the University of Florida. He received his undergraduate degree from Rice University and then his Ph.D. from the University of Colorado. And then after that had 2 postdoctoral fellowships, one at the European Southern Observatory in Munich and the other at the National Radio Astronomy Observatory in Socorro, New Mexico. And he came to the astronomy department at UF in 2019. His research is directed toward understanding the formation of stars, massive stars. And he teaches courses in observational techniques at the introductory and advanced levels. And I always check out my speakers on Rate My Professor, and he is described as awesome. So today he will be speaking about where stars come from. Hopefully that's what it's, yeah, thanks.
All right, yeah, so I am going to tell you a little bit about where stars come from, how they form. Last time you learned, if you were following this, you were supposed to learn about what stars are and what their life cycles are. I'm going to talk about the beginning parts, but I'll start off with just a little bit of introduction. I am leading a research group at the Department of Astronomy with, it's a fairly large astronomy group, so 6 graduate students and a postdoc. And we're standing in this picture in front of a picture of the center of our galaxy. And my students like to have a good time, so they put sunglasses on our pictures when possible. So this is my group, and I'll be telling you a little bit about what I do and a bit about what they have also been studying. So this is also a talk about our galaxy, the galaxy we live in, which is the Milky Way. And okay, I'll tilt this up a bit. Okay, so I'm going to be talking about the Milky Way, our galaxy, and what I'm showing you in this image is a picture of the whole sky. So at the center here, that's the center of our galaxy. On the outsides, that's the anti-center. It's backwards behind you. And what we're seeing in this image is something you couldn't see with your own eyes. It's what's seen by this observatory, the Planck Observatory, which was it's a space observatory that completed its mission several years ago. And combined with data from this telescope, which is a 100-meter telescope, so you can't quite get a sense of scale here, but that is a football field across, that it was mapping out all of the gas in our galaxy. And so I'm going to use this image as sort of the guide, the context image as we go through and take a tour of the galaxy. So the story of star formation, where stars come from, starts with the fact that when we look for stars, we can tell that some of them only have lifetimes of less than 10 million years. And that's, okay, 10 million years might sound like a long time, but we know that we've been around much, much longer than that. So if we see stars that have lifetimes that are much shorter than the age of our solar system, we know that they had to have been born very recently. And of course, the starting point here is that we know the age of our own solar system and our own sun very precisely. It's 4.5 billion years old. So I got right gigayears here, which is about a third of the age of the universe today. So our sun, we understand very well. We can measure very precisely. When we look at other stars, we have to jump through a few hoops to understand how old they are and how long they live. So I'm going to give you this one brief overview of the whole story of a star's life in one slide, and then we're going to go into this in a little more detail. So the starting point is a molecular cloud, so a cloud of gas that is heavy enough that it can collapse under its own gravity to form a young protostar, which eventually turns into a star with a disk, that starts doing some exciting things I'll tell you about later and clears out its environment until it's just a star on its own. Then once the star is done forming, so this part here, the top row, is the formation process. It's how it's going from just an empty cloud of gas to being an active star. Then it goes through the whole lifetime of being a star. So the Hertzsprung-Russell diagram you may have seen showed this, but you start off with a young star, then it spends a long time being like our sun. So all these yellow circles are the main sequence. So that's stars like our sun. Then it starts to get older. It gets bigger as it gets older and eventually dies and finally becomes a white dwarf. So all of this stuff, I'm leaving that was last week's talk. I'm going to focus in more on the part here. How do we go from a gas cloud to a star? And what does that look like? So what we've learned is that young stars, so the youngest stars, show up in nebulae and in dark clouds. So this is an image of Ophiuchus, which is a constellation. If you look at it in optical light, so just the same light your eyes can see, but with much, much more sensitivity, basically with a very nice telescope at a very dark site, you could see something like this. So you see the bright clouds here are nebulosity, they're nebulae, they're gas that's being lit up by stars. And then the dark stuff here is cold dust that's absorbing background starlight. And places like this are where we find young stars currently forming out of the interstellar medium. So interstellar medium, just break it down for a second. Interstellar means between the stars, and medium just means stuff. So we're just talking about the stuff that's between the stars. So the stuff that's not stars, some of it becomes stars. Okay, so now we're back to this view of the interstellar medium, and I'm going to show a little movie here. We're going to zoom into the center and go from that all-sky view down toward the center of our galaxy, and we're looking at a bunch of different wavelengths of light here. I'm going to show you this movie again later, so I'm going to skip past that for now and show you what the interstellar medium looks like. We have images that look like this. So this is an image taken with a number of different telescopes, some from the ground, some from space, all at wavelengths we can't see with our own eyes. So this is infrared and radio and millimeter telescopes. And in this image, the orange stuff, that's where new stars are going to form. The purple stuff is where stars have blasted out radiation and high energy electrons and photons. All sorts of interesting things going on here. This is the center of our galaxy. I'll tell you more about that. But I want to tell you really the story of how stars form as we go first. And what we know is that young stars are found in these dense, cold, and dusty regions. And this actually took us a long time to figure out. The image I'm showing you here is from the Spitzer Space Telescope, which was operating from roughly from the early 2000s to 2010 or so. This observatory mapped out our whole galaxy, the whole Milky Way galaxy, in infrared wavelengths, so from 3 to 8 microns. And it made these wonderful color images. Of course, this is a false color image, but what we see in the image here is this dark, maybe seahorse-looking structure, which is the place where there's cold and dense gas and dust in which young stars are forming. So the technology that let us figure out what's happening with young stars was these infrared observatories, which lets us see where stars that are not quite as hot as the sun exist and where they're hidden away by this dust. So the Spitzer observatory gave us this look where we can see the dark clouds as dark. So we see the cold stuff as the black features in the image. The Herschel Observatory then came along and looked at even longer wavelengths. So we're talking about millimeter wave, so similar to maybe what you'd expect from, if you're going through the airport, the TSA millimeter scanners, they're using similar wavelengths as the Herschel Observatory. So this is Herschel, this is Spitzer. Herschel operated from 2010 to 2015 or so. And everywhere we saw the cold, dark dust lanes in the infrared, we start to see bright, glowing emission in the far infrared. And so these little spots here are where there are young stars just turning on in their birth clouds. We can look at other dark clouds again. So the top part of this one is showing you what we see with the Spitzer Space Observatory. But now you can see this is a kind of a blurry image of this little region here. When we zoom into this, this is now what we see with the James Webb Space Telescope. So that's our newest one, and it has much better resolution and better sensitivity. It's a really great observatory. And what I'm showing you here is actually an image from my own research where we looked at this dark cloud, and we were looking for these sites of star formation. So we can still see there's a dark cloud here, right? The dark cloud is showing up. That's the stuff that's going to form new stars. And what we see is the new stars bursting out, shining their light out from within that cloud. Now, I study, and what we're talking about here is the interstellar medium, the stuff between the stars. So in this image, you can see all these bright points of light. Those are all stars. We want to get rid of the stars so we can study the stuff between them, study the stuff that's going to make new ones. And so when we remove the stars, we get this much more eerie and wispy looking set of clouds where we only see the clouds themselves and the bright light that shines out from those young stars. Now, of course, we also have this dark spot here. This is where we can't even see the young stars yet. They're still coming. Okay, so how do we find young stars? How do we know that they're young? Part of it is from watching the process of star growth from the beginning. And young stars have to grow, they have to eat, and they're very messy eaters. They shoot out these jets or outflows. They shoot material out from them while they're accreting, while they're gaining their mass. So in the center of this image, right in here, is where a young star is forming. And you can see it's shooting out a little bit of extra material to either side. Most of the stuff that's falling in, most of the gas cloud is falling into that star, but a little bit gets shot out in both directions. So this image is an infrared image in just one wavelength. They just color-coded it to be orange. This is another infrared image now from the James Webb Observatory again. And we know that there is a young star forming right in here because we can see the stuff that it's shooting out. But the star itself is hidden by a disk, by a bunch of stuff that's going to fall into the star. I'm going to tell you a little bit more about disks because they're an important part of how stars form and where they come from. So we can see disks in a number of different locations. And if you look at the Orion Nebula, so I hope you've all heard of the Orion constellation. If you look just below the belt, there's a bright nebula there. It's our favorite place to look with space observatories because it's very bright. And so the Orion Nebula looks like this. It's this bright blue haze that you see everywhere. Sometimes there are a couple spots like this one where we see a dark lane right in front of that bright background light. And when we see that, those are places where there are young stars forming. So the dark stuff is the dust that's going to fall into the star, but hasn't yet, blocking out the background light. And then you see a little bit of red coming out to the side. That's a little bit of the starlight coming out from where that young star is. So these things look really quite impressive when you look at this. Is the Hubble Space Telescope showed us this one. And we have lots of images like that. There's a class of objects that have the funny name proplyds. There's no particular meaning to that term, but it's these objects where there's a young star surrounded by dust and sometimes being illuminated from one side. So the disks here, those dark dust disks, that's the material that's falling in to the star. It's what the star is growing up from. So we can look at these disks, not just from the starlight they block out, but from the starlight they re-emit. So when they absorb the light that we see with our eyes, they absorb optical photons, they re-emit them at longer wavelengths. They glow if we look far enough into the red. And when we do that with telescopes like ALMA here, so this is the Atacama Large Millimeter Submillimeter Array in Chile. It's a collection of 50 dishes that are each 12 meters across, so a whole bunch of big dishes. We combine their light together to make images like this one, where we can see this spirally disk of material surrounding a pair of stars that are each themselves surrounded by little disks as they're growing. So we see the disks directly when we look at millimeter wavelengths, and we have different filters we can use. Even there, some of the filters show us where the gas is. So in the blue over here, we have a very big spirally looking disk of gas that's falling into the stars slowly. But when we zoom into the center and we look in the orange there, we see where the dust is. And all of this is material that most of it's going to fall into the star. Some of it's going to get flung out as like, it's the messy eater. It's throwing some food on the floor. And some of it will end up in planets. So this is the best image we've got of a disk around a young star. This is the HL Tauri system, so it's in the constellation of Taurus. And what you can see when we look in real detail at the disk is all of these dark bands and light bands. And that's telling us that the disk is not this homogeneous, smooth thing. It's not like a dinner plate. It's got a bunch of holes in it. And some of those holes may be the sites where new planets are forming. So the star formation process, where stars come from and where planets come from, it's the same thing. When stars form, planets form. So we can also look back at optical and infrared, so the shorter wavelengths of light, more like what we see with our eyes. And when we do that, we still can see the disk, but what we see is something a little bit different. We see scattered light from the surface. So in the middle here, that's where the ALMA light was coming from. And from the surface, it looks like a bowl. You could imagine there being a bowl in here because the disk is kind of bowl shaped. And this is what you get when you look with telescopes like this one. This is the Very Large Telescope, very aptly named, also in Chile. This one is run by the European Southern Observatory. So just to tell you what we're seeing here, the left side is reflected light. So you can think of it as a dirty mirror. It's not very good at reflecting light, but it reflects some. Whereas when we look with ALMA at the emission, that's like as if it's a light bulb, though a very, very cold light bulb. So we have these beautiful galleries of lots of disks around young stars. So we know that all stars form with disks around them, but the disks can be different sizes, they can be different shapes, they don't look the same. And some of that is because of planets forming, some of that is because sometimes stars form in binary systems. So they're two stars forming together. Excuse me. So there's a wide diversity of how stars look as they're forming. So as I said, when you have disks, that's where planets form. And we can see now with some of our latest observations, we can actually see young planets forming in the disks around stars. So this here is a protoplanet. It's a planet that is still starting to form. And the way that planet formation happens is it's part of the same process that's forming the star. So we have that disk would just stay there forever if there wasn't something that drags stuff in. Just like we, the Earth, orbit the sun, and we're gonna be orbiting the sun pretty much forever until something comes along and moves us, all that stuff in the disk would stay there unless something pushes it. And so what pushes it is that there's dust, and the dust tends to settle out while the gas stays high. So these are edge-on views of disks. So you imagine that you turn this 90 degrees, you're seeing it this way. If you turn it 90 degrees, you'd be seeing a plate, be seeing a nice clean circle like I was showing in the other slides. And so the dust settles to this thin midplane while there's a bunch of gas and stuff that is above and below the midplane where we see the scattered light. That makes our bowl. So there's the bowl part, there's the plate part, and the plate part is where planets form, and it's where the stuff gets pushed into the star. So the way planets end up forming is they get stuck in these piles of dust, and the dust collects together. It's a complicated process we don't fully understand, but we have a pretty good idea when we look at asteroids in our own solar system. We've visited a few of them in the last decade. They look like this. This is asteroid Bennu, and it is a rubble pile, right? It just looks like a bunch of rocks kind of barely holding together, which is roughly what it is. And so this is what we think early planets, the planetesimals, the things that are going to become planets like Earth and Mars and Venus, they started out as things like this and had to collide, had to build up as they collected together. So these things, though, these planets, the planetesimals, that's all the detritus left over from the star formation process. Almost all of the gas, almost all of the dust that we see is actually forming the stars, not the planets. The planets are just a small part of the total mass that's making new star systems. We can see some of the debris from planets colliding with each other when we look around certain star systems. So this is a kind of a funny image here where there's a ring of material, so it's like the disks, but we blocked out the star. So this hole here that's not really what you would see. This is because we had to block out the star. It was too bright. But this ring of material is showing where probably some planets smashed into each other and didn't stay together. They just turned back into dust long after they were formed. Okay, so we're back to the question, though, of where did the stars come from? How did this process start? Well, most stars, probably even including our own solar system, formed in clusters or groups. So when I say a cluster, I'm going to give you more examples of this, but I mean there were a lot of stars. You can see all these stars here. There are more stars in the center than on the outside. They're all in the same place where there's this interstellar medium. There's the fluffy stuff around here. They all formed together. They formed from the same parent cloud, and they formed close to one another. So this is a relatively small cluster. We can see other clusters that are much more impressive, where there are just a whole bunch of stars. This one actually has of order 1 million stars, all contained in an area of space, a volume of space that's actually smaller than the distance from us to the closest star today. So right now, the distance from us to the closest star, where it's about a parsec, a few light years. In clusters like this one, we cram 1 million stars in that same volume. So it's a very different environment than where we live today, but this might have been the kind of place where the sun was born. And indeed, massive stars, which I'll tell you a bit more about now, they're stars that are bigger than the sun. They pretty much all form in clusters like this one. So these massive stars are very important because they produce most of the light that we see in galaxies. So when we look at images like this one, these are images of nebulae. The bright blue holes shown in here, those are areas where stars are massive stars are making a whole bunch of light. These are the young stars that only live for a few million years. They're illuminating these holes in the gas. And if we look at other galaxies, and this is the only time I'm going to show you galaxies other than our own, when we see other galaxies, all the spots that light up, all of those bright spots, those are lit up by massive stars, by stars that are 10 times bigger than our sun, or even more. So with James Webb, we get to look again at these massive star clusters, and this is one from just earlier this year from actually some of my own research. This is one of the most massive clusters in our galaxy, and with James Webb, we can see first the stars, and you can see there's a little bit of gas around here as well. But if we can change wavelengths, we have lots of different filters that we can put in with James Webb, and when we go to different set of wavelengths, we see all of this gas being blasted out from the massive stars around here. So you see all of these little cloud features pointing back into the center. They're all being blown away by the very bright, very big, massive stars at the center. So coming back to the Orion Nebula is also forming a little cluster, and this is what James Webb sees when it looks in Orion. Again, we can switch filters. So in this image, in both of these images, you can see there's lots of gas around. You can see lots of stars. The Orion cluster is not such a big cluster, but it has a lot of pretty things going on. And one in particular is this feature up here. So I'm switching from the James Webb Observatory to the Gemini Observatory. So this is a big telescope. It's 8 meters across on the top of Mauna Kea in Hawaii. And we use that to image this thing that I'm showing in the bright orange. I'm going to zoom in on that for a second, which is because this is one of the weirdest things we see at sites of star formation. We see this big explosion. Now, explosions we usually associate with the death of stars, right? You have probably heard of novae and supernovae. That's how stars usually end their lifetimes. They blow up. But it turns out that even when they're forming, They live in these really dense clustered environments. So there are lots of stars packed in together. Sometimes they interact. So you have two stars that come really close to each other. And it appears that sometimes that can drive big explosions. And so what we know about in this, this image here, all of these little fingers, these arrowheads pointing away from the center down here, these are the gas that's been blasted out when there was something that happened about 500 years ago. We don't know exactly what happened. We have some ideas about it, but it probably involved a multiple star system where all the stars were stuck together and now they're flying apart. So there was an explosion, it shot out a lot of gas, and all the gas and dust, most of it's still stuck in the center, but the stuff that got flung out is now really lit up. So we know that the star formation process isn't always smooth and clean. Sometimes it's very violent, explosive, and exciting. It makes for these sorts of beautiful images. I told you that stars form in clusters, but I also stars form in multiple systems. So most stars, if you count the number of stars, are in binary systems or greater than binary systems. And so this is an image showing you, if you look at each individual star that you can see, it turns out every single one of these stars is many stars. And we don't know that until we zoom in a lot. We have to use different types of technology. We have to use things like interferometry to figure that out, because the stars are too close for us to resolve. They're too, if you look with your eyes, you only see one star. If you look with a telescope, you start to see two. You look with a bigger telescope, you then see four, and it just keeps going. We just keep finding more and more stars packed into these systems. So most stars live in multiple systems, but most star systems are single. It's a very hard thing to wrap your head around sometimes, but so our solar system, it's not that uncommon for a star to be the only star in a system. But if you wanted to figure out where most stars were, they're mostly going to be in these more densely packed systems, like in this image. So I'll also highlight, this is again from the Very Large Telescope, but they use an interferometer. So this is a very new instrument that only came online a couple years ago. Okay, so the story of star formation, as I've told it so far, is there's gas, it collapses into to stars. How does that actually happen? Well, we can't watch movies of it happening, but we can simulate them. And so this is a movie of a hydrodynamic simulation. So that somebody put in a lot of physics into a supercomputer and let it run. And this lets us watch what happens to the gas as it collapses under its own gravity and begins to form a cluster of new young stars. So we're just going to let this go for a minute. You can see the little white dots appearing. Those are the young stars, and they're appearing at the intersections between these long linear features that we call filaments. And some of the stars, as you can see, get shot out. So the stars interact with each other, they spin around. Some of them get flung out, so they stop growing. The ones that stay at the bottom, they stay in the bright yellow regions. They get to keep growing for a long time, and they stay stuck together in these clusters. And so we can see now as we zoom back out, that's the whole cloud. And when you do simulations, when you run your toy model in a supercomputer, you get to spin it around and look at it from many different angles. So as observers, when we work with real data, we don't get to do this, unfortunately. We can't send our space telescopes out of the galaxy. But so we have to reconstruct what these things might look like. Okay, so this is showing you what a whole region of star formation might look like. I also want to show you what disks look like. So if you zoom into each of those individual star particles, they're making something like this. And this is actually another movie where what we're going to see is one at a time, each of those panels is going to populate, and they're going to jitter around a little bit. Because what we're seeing is the formation of disks. So this is stuff happening on much smaller scales. And every time you see one of these windows pop up, that's when a new star formed. A new one of those white dots appeared in the previous movie. And they start off where there's just a little bit of mass in the star, a little bit of the gas has made a baby star, but then they keep growing. They keep gaining more material from their surroundings. And sometimes they're in binaries, which is why you get the jittery ones. That's when they're trying to follow two stars that are moving around each other very fast. And others just have nice, smooth, slow growth. And some of them get flung out completely, and so they don't have anything around them anymore. So again, there's a huge diversity of how these things happen, but you can get to see all the sorts of interactions that happen between stars and their disks. And we get to see snapshots of all of these things, because these processes, what I'm showing you, the movie that I show here is sped up by many, many thousands of times, right? The process of going from a gas cloud to a young star takes roughly 1,000,000 years. So these are sped up so that we can see the entire growth of a star happening only in a few seconds. So I will show you one more movie, and this one is meant to highlight the messy eating part of the process. So we start off with our molecular cloud again, the same sort of initial condition, but now you start to see these jets of material being flung out. And we get to see how when the messy eating process actually kind of messes up the situation for other stars. So if one star is shooting out a bunch of material as it's growing, it's blowing away some of the gas that other stars would have gotten to grow from. And you can start to see bubbles. So these bubbles up here are coming from the massive stars. So the process looks very similar to the previous movie, but as we learn more about the physics, more about all the things happening, we get to see how it's a more and more complex process the more we learn. So this is still very much a field of research where we're learning new things every day with new telescopes and with new simulations as well. So at the end of this, we're going to see the very end, there's a supernova that's going to blow out all the leftover gas, and that'll be the end of star formation in this particular cloud. You can see there, got a little grainy, but everything got blown out at the very end. You can start to see the holes through the cloud. It starts to look a little bit more like empty space. And it looks like a star cluster once you get to the stage. Okay, so this is roughly the last I'll be showing you of simulations. I'm going to go back to the real images, the real things we look at with telescopes for the next bit. So I showed you this image before. This is in the constellation of Cepheus. And this is one of those areas where we have those high mass stars. Massive stars living in the center here are blowing away the gas. And you can see it looks like there are these fingers pointing back to the center because the massive stars have blown holes into our gas cloud. We see this same sort of thing all over the sky in different ways. So over on the left side, this is an image taken from the ground, taken with a 3.5-meter optical telescope. And you can see there's a dark lane. There's a star, massive star forming in here, and it's blowing material out and lighting it up as it goes. On the right side, this is a James Webb image from one of my students that we have just been working on recently. It still has some blips we have to clean up. But this is a very high mass region where you can see the bubble being blown out. You can see the dark lanes where there's still cold gas. Everything is happening all at once in star-forming regions. So I'm going to take you now to the galactic center, the center of our galaxy, which is the richest and most intense place of star formation in our own galaxy. So I showed you this image before. We have the orange stuff, that's the cold gas clouds where new stars are going to form. But I want to put this in context, and I'm going to show you, again, the all-sky image. So when we look at the whole sky, the galactic plane is this middle part here, so that's our galaxy. That's the Milky Way. We're going to look at the center, which is called the central molecular zone. And I talked about Orion before. It's over here. So the center of our galaxy I'm going to now give you this cartoon picture. So this is what we think our galaxy looks like if you look from above. We can't take a picture of our galaxy from above. There's no way for us to do it. But we've been able to make this cartoon up. And so an artist drew this one. And so what we think is we have these spiral arms, so these spiral features that go toward the center, and there's a bar. So you can kind of see there's a linear-ish looking feature here. And if you zoom into the center where there's this convenient orange box, that's a really, really small fraction of the volume of the galaxy. And it's 0.01% of the volume. But it has about 10% of all the star formation that's happening in our galaxy today. So even though there's star formation happening all throughout our whole galaxy, a huge fraction of it is concentrated in the center. So the center of our galaxy looks pretty crazy if you look at it at different wavelengths. So this is an image now made from the Meerkat telescope in South Africa. And what you see in all of these bubbles here are showing supernova remnants. So that's what all of these things are. So those are the places where massive young stars died in the past few 10,000 years or so. In the center, this is where the black hole at the center of our galaxy lives. We can't see the black hole, but we can see the stuff around it. And all this other stuff, these very thin, narrow filaments, are things we don't really understand. They're probably related to magnetic fields, so just magnetism, but we don't know where they come from in detail. It's still a topic of study. The young stars are forming in regions like this over here. So where you can see these little stars popping out. Those are where new young stars have just formed. So I'll give you the all sky view again, show you our galaxy in context as a whole. So we're going to jump through a couple different wavelengths to set the stage here. This is optical light. So this is what you would see with your eyes if your eyes were absolutely perfect. This is an image made from the Gaia Observatory, which mapped out 1 billion stars in our own Milky Way. And what you see these are all stars. Here are the neighboring galaxies, the Magellanic Clouds. All of the dark stuff here, that's the dust that is the Milky Way, right? These are the dust clouds that block out starlight where young stars are forming. Up here, this is Ophiuchus, and here's the galactic center. When we go to slightly longer wavelengths, so we go from optical, where we see, to near infrared, just a little past what we can see with our eyes, suddenly we can see stars everywhere. So right here, we're missing the stars in the midplane of the galaxy. Here, we start to see there are many, many more stars in the middle. We still see dust lanes, but the dust is less impactful at these wavelengths. So this is the 2-mass observatory. Now we go back to our Planck and radio image of the galaxy, showing that all the gas lines up where we saw those dust lanes before. And we can go to other wavelengths as well. We look in the X-ray. So we have X-ray observatories. Actually, this is gamma rays. This is the Fermi Gamma Ray Observatory. The galaxy just lights up in gamma rays, and we don't know exactly what causes all of that, but wherever there is gas, we see gamma rays. When we look in X-rays, this is one of the interesting things. If we look at the whole sky in X-rays, we see these big bubble features toward the center of the galaxy. And these bubble features, which we have to show in false color, of course, because they're X-ray images, they come out of the center of our galaxy, right? They're centered right on the middle. And so I'm showing you just different ways of looking at X-ray images. These bubbles trace back to the center of our galaxy. So they might come from our black hole, or they might come from the young stars that have formed there. And even in gamma rays, we see the same feature. So gamma rays, of course, are very, very high energy photons. So it takes something very energetic to do this. But it's still debated what is actually causing these big bubbles that we see on the sky. When we can zoom in and we can see that they come from quite close to the very center of our galaxy. So one of the things that I'll tell you a bit of my research is we study the center of our galaxy, mostly looking for stars, for new stars forming. And so we've done this survey with ALMA, the Atacama Large Millimeter Array, and we have to come up with clever acronyms for all of our survey names. So this one's ACES. don't have to worry about that meaning. But what we're looking at is this millimeter wave emission. And one of the things we can do when we look in millimeter wavelengths is we can see the motion of gas. So what I'm showing you in this image is we've got red stuff and blue stuff, which is color-coded to tell you whether it's moving toward you or away from you. And the key here is that we're using the Doppler shift of emission lines. Just as, so, okay, the color code here is these cars are moving toward you in traffic, these cars are moving away. Same deal here. We're not using radar, of course. We can't shoot out our own light. We're just depending on the light that we receive from the stars and the gas. But we can do that with very high precision, only a few meters per second. So we could tell if you were speeding in the galactic center. Now, the gas is always doing that. It moves around very quickly. So we can make these sorts of images to map out the velocity, the motion of the gas. And when we've done that, we found, now I'm reporting on one of the cool discoveries we made. So this is an image from that survey. Now I'm showing you real astronomer coordinates, so you don't need to worry about that. We found this little dude in here. This just a blip, looks like a dot, doesn't look like anything special. The reason I'm showing you this one is because when we look at its spectral lines, it turns out it is doing something special. It's moving really, really fast. There's a lot of stuff that's moving fast in either direction. So you don't have to worry about the plot here. I'm just showing it to you because we don't have anything more to show about this guy. But this broad line feature, broad emission feature, comes from this guy, and we don't know why. This is just an open mystery. It's something we discovered last year, and I'm just telling you that there still exist mysteries in our galaxy. And so what we came up with is this little graph chart, which you don't need to worry about much here. But the green means that this hypothesis is favored by this piece of data. The red means it's disfavored. And if you take the time to look through this, you'll notice that there's no hypothesis that's all green. So we have ideas for what might be going on here, but none of them are certain. We don't know what it is. So we're still discovering new things. And what we're looking for was star formation. We wanted to find young stars forming in these gas clouds. What we found was something. Okay. So the last place I want to take you a little bit here is the Orion Nebula. So we're looking at the center of our galaxy in the galactic plane. Over here is Orion. So I'm going to move that to the center. So the Orion Nebula that we were looking at a little bit earlier is near the galactic plane, but not on it. So you see this, the white haze here, that's the galactic plane. And if you were looking at Orion, this is how it would look on the sky, a little bit weird. So in the Orion Nebula, or the Orion constellation, rather, there are these dense molecular clouds where the young stars are forming. And we have, in particular, when we zoom in to this little spot here, we have this thing, which is aptly named the integral-shaped filament. Looks like an integral sign. Okay. That is where this explosive outflow that I told you about resides. It lives right in there. And when we looked with ALMA, we saw the explosion in more different colors. So it's an isotropic explosion. It's going out in every direction roughly equally. But I'm showing you this again because I want to tell you about a different discovery we made at the center of this explosion. We learned a little bit about the things that came out of it. And what we found is that one of the objects at the center of the explosion is this thing, which is a disk. We can't see the star because the star isn't glowing at this wavelength. But this is a disk, and this disk is unique in that that blue glow I'm showing you is from a particular molecule that you have all heard of because it's salt. It's just ordinary table salt that's glowing. We don't normally see salt in space. You can see it in Io, the moon of Jupiter, but most of the time we don't see salt in space at all. So it's a very strange find to discover salt in a disk at the center of this region. We actually still don't know why it is, but we know how to use it because we can use the kinematics, the orbital motion of that disk to tell us how much mass is there. That's how we weigh the stars. So just to give you a sense of what we're doing, because this is the current research, is we look all across the galaxy and we find other stars, other young stars that are forming. You'll note that they're all in the inner galaxy, in the midplane. These are all of the other salty disks we found. So we've been finding these salty disks out there. Now, these look pretty blurry Don't worry, it's not your eyes, it's the telescope. These are far away, so it's hard to see what they look like in detail. Only this one actually looks like a disk, but we're pretty sure by using that Doppler shift technique that they are. Okay, so I'm gonna now show the movie where we zoomed in to the center of the galaxy. I'm gonna let that go for a minute so you can just see some of the details of what we've been able to learn as we use higher resolution and just better telescopes over the years. So I stopped it at this point before, but now we're gonna zoom in even further, and you're seeing all of these spots are where young stars are presently forming because there's new gas and dust that hasn't yet collapsed, is still in the process of collapsing. Now, this is a region where you can see feedback, where you can see the nebula being lit up. But this is the stuff that's very new that we haven't even published yet. So you're getting to see it before anybody else does. And so we're proud of these images. We're going to keep trying to make them better. Okay. But as we zoom back out, this is our galaxy. This is where stars form, and they're coming from that gas. So I'm going to leave it here and stand open for any questions you guys might have.
Well, that's very interesting. Very well presented. I have a question, if you don't mind, if you all don't mind too much. So in that thing where you were showing all of those brand new stars, many of them were rotating or moving. And they seemed like they were orbiting in a kind of, some of them were sort of twisting, and they seemed like they were setting up an orbit in a regular sort of way. What's making them do that? And why is it regular? Some of them are moving very fast, I think.
Right. So that's sort of a selection effect in the sense that if they weren't in orbits, you would just see them go in and go out, and then they'd be out of the movie. They'd be done. So you only get to see the ones that are actually entering orbits. So why do they enter orbits in the first place? Well, there are a couple different ways that happens. One is if there's a big enough disk that, so I talked about planets form in disks. But if you have a big enough disk, instead of forming a planet, you can just keep growing it. And if a planet grows too much, it becomes a star. And then the reason is that you had your star there, you had the disk, and then a star formed in a disk, and it was already in a regular orbit. So that's one way that can happen, the sort of regular orbit. That's common. We know it happens, but it's not the only way. The other way is through you have two stars that are formed independently, but they both still have a bunch of gas around them. And they come together, and there's enough gas around them that instead of just flying by each other, they stick. So it's a sticky collision instead of just a flyby, and they end up capturing each other. That sometimes requires having many stars together, but when you have a star cluster, that sort of interaction can happen. So there are two different ways it happens, and we know both of them work. So through disks and through capture.
Any other questions?
You talk about the dust falling in, but of course, are you talking about gravity, mass attracting it? What's the falling that you're describing? And the other side is, of course, you say currently, we're looking back a long time. So how far back are you looking where you're seeing these stars forming?
Okay, so we'll start with the first one. So it's gravity. Gravity is what's pulling them in. The trick, though, is that gravity is pulling us into the sun, right? We're sitting on Earth. Earth has been orbiting the sun for 4.5 billion years, and we're being drawn in by gravity. So we need something more than just gravity to pull us in. We also so if we're talking about the dust and gas that's falling in, something more than gravity has to happen. And it's essentially a type of friction. So if you have enough dust and gas, the gas and dust rub against each other. Some falls in, some goes out. But it's fundamentally, it's gravity pulling it in and friction helping dissipate the angular momentum. So the other part of your question was, how far back are we looking? And there are multiple different answers because we're looking at different distances, and how far back in time we look depends on distance. So the Orion region is about 1,000 years ago. So I should clarify, when I talk about something happened 500 years ago, that's 500 years from our perspective on Earth. Really, it's 500 years plus the amount of time it took the light to get to us. So that would be 1,500 years. But when astronomers talk about it, we always use our own frame of reference. The most distant things I showed you today within our own galaxy, the galactic center, is about 25,000 years ago. So these are, that's a very long time, but it's actually fairly short on the time scale of stars, right? As I said, stars tend to take 500,000 years to form, roughly. So it's relatively short compared to that, but certainly long compared to an astronomer's lifetime.
Very interesting. I'm interested in understanding a little better how you're getting all these pictures and who else is looking and that sort of thing. How many universities have the capability that UF does? How much does UF have invested in various telescopes to get the time to do what you're doing? And how much does all this cost?
Well, so a lot of universities, okay, let's see. How many universities have UF's capability? In the US, 24, about roughly. And 30 or so universities are on our level or comp. Worldwide, probably double or triple that, mostly in Europe, but growing more and more in China recently. So then your question was about investment. Well, UF has not invested a whole lot in astronomical instrumentation over the last decade and a half. Mostly, I was showing you images that were mostly from space observatories. And so UF is not directly investing in that. We're benefiting from the federal government's investments in these space observatories, and also from ESA. NASA dominated space for a very long time. But in the last few decades, the European Space Agency has really caught up. And so one of the slides I showed you was the Gaia Observatory, another was Herschel. Those are ESA based. So how much do they cost? Well, the most expensive telescope in total amount of dollars was the James Webb Space Telescope. And its total budget over 30 years or so ran to $10 billion. But those $10 billion are basically paying people who are figuring out how to build the technology, how to develop the technology, how to get it launched and all that. Right now, it runs on a budget of about $100 million a year, and that funds a few thousand astronomers and a few hundred engineers whose job it is to make sure it keeps working. So because it's way out at a Lagrange point, so it's pretty far from Earth. So the total cost of astronomy across the globe is, actually, I don't know that number. You could probably find it, but I don't know, maybe it's $1 billion or $2 billion a year. And that's something like 10,000 to 20,000 astronomers around the world actively who are active research astronomers, including graduate students. So it's those are maybe big numbers, but small compared to almost any other field, I think, field of research you might talk about. Did I cover all your questions?
So you showed some pictures of material shooting out from star formation. It's kind of related to an earlier question that she asked. What determines whether the materials shooting out are coming in? I mean, I always assumed it all came in, but obviously that's not right. And it looked like the stuff shooting out, I'm sure this is an artifact. It looked like the volume shooting out was actually bigger than the star, but that may be an artifact of the picture. But what causes it to go up rather than go down?
Very good question. And so and this is again another real topic of research where we understand some of the processes. So the short answer is magnetic fields. So what happens though is that something like 90% of the material falls into the star. But in order for it to do that, you have to have it has to lose its angular momentum, because if it had angular momentum, it would just keep orbiting around. So where does that angular momentum go? Well, it turns out it gets shot out. So that stuff that's shooting out is necessary. It's a necessary part of the process for stuff to fall in, because you just have to conserve the total angular momentum. Now your question about it looked like it was bigger than the star, it is actually, because the material that's getting shot out is coming from the disk, not from the star. So the disks are much bigger than the star. The innermost part of the disk is 100 times bigger than the star. The outer part is a few thousand times bigger. And so what needs to happen is for stuff to go inward, something has to go out. And what happens is it goes out, the stuff that goes out is going out much faster. So the same amount of mass carries more angular momentum away in the outflows. And that which lets the other stuff go inward. So that's sort of fundamentally the physics, the mathematical balance that happens. How exactly the process happens in detail, like how does a particle know whether it's going to go in or out? That's still a bit of a question of, well, did it get lucky and land on one magnetic field line, or did it go on the other one? And the details of how those magnetic fields are shaped and where they come from, still very much a topic of study. And there are answers, but they're not easy to summarize, and they are controversial still.
There's a question relevant to this in Zoom. It says, what are the gases and dusts made of?
Okay.
And where does it come from?
Right. So almost all of the gas I was showing you, all the gas is hydrogen by mass. The most of the gas in the universe is hydrogen. 70% hydrogen, 30% helium, and a trace amount of everything else. But the images I showed you actually mostly come from those trace elements. So I told you salt, NaCl. Those are very, very rare elements by mass and by number, but they glow, and they glow at particular wavelengths, so we can see them. Carbon monoxide, CO, is actually the most common thing we look at. Most of the images we make of gas are carbon monoxide. Just the coincidence of physics, it tends to make really bright lines that we can look at, from the ground. So we don't have to go to space to look at them. So where does it all come from? Well, the hydrogen and the helium is primordial. It's been there since the Big Bang, since the beginning of time. All stars in the universe form from that primordial hydrogen and helium. All the other stuff came from stars that died. So supernovae or the dying red giants, they blow off the heavier materials. All the stuff we're made of, we are star stuff. That's the Sagan quote. And all that stuff that makes us up, most of the stuff in this room came from supernovae and dying normal mass stars. So dead stars and primordial stuff.
And the other question on Zoom is, do other galaxies operate in the same way as the Milky Way in formation? Didn't early galaxies around the time of the Big Bang operate differently?
So short story is, it's roughly the same. All the processes I told you about, gravitational collapse, the formation of disks, dissipation or loss of angular momentum, all those physical processes were the same. But galaxies did look different back in the early universe. The galaxies as a whole were much smaller. So I showed you the center of our galaxy had 10% of the star formation. But in early galaxies, the center, that same volume, probably had 100%. It was all concentrated into a much smaller area. So there was a lot more interaction happening. It was probably a lot more violent. But the physics, the processes were essentially the same.
Right.
A couple behind you.
There's one right over here.
When you say dust clouds, I can imagine dust clouds on Earth. But what are those dust clouds like, the density of them? If I was in the middle of a dust cloud, what would it look like?
Good question. So the dust clouds we're looking at are many, many, many orders of magnitude less dense than what you would think of. But they're composed of somewhat similar things. So, if you imagine, unfortunately, a cloud of ash, like from forest fires and such, those a lot of the ash is comprised of polycyclic aromatic hydrocarbons. And actually, if you grill anything, the black stuff that is pHs, a lot of the dust that we see is actually made of that. We don't know exactly how it formed, but that's the topic of astrochemistry. We're learning how it comes about. But yeah, so dust is that stuff plus just sort of silicate grains. So okay, that's a technical term. Sand. It's basically sand and sticky carbonaceous stuff. And that just coagulates together. But it is very, very, very low density. You wouldn't notice it. You couldn't breathe it. You'd best think of most of the clouds I showed you as being closer to a perfect vacuum than you could achieve in almost any lab on Earth. Now, you can get close to it, but they're really, really low density. Where that changes a little bit is when you look at those disks, the mid plane of the disks where you start building up planets, those start to get to be kind of like what you would think of as maybe the outer atmosphere of Earth. Still very, very low density, but it's getting to be more like something you would recognize as cloud. The reason we can see these giant, these very, very low density clouds is they're, even though they're super low density, they're still a million times more dense than the other stuff, the harder vacuum around them.
On one of your slides, you had a question mark after dark matter. And I was wondering, given that you really can't measure the impact of dark matter directly, how might it play a role in the formation of stars?
So in modern star formation, we think that dark matter plays no direct role. It only plays an indirect role. So dark matter is just any mass that we can't see, and it's essential for shaping galaxies. So if our galaxy did not have dark matter, it just would not look the same. You would not see those spiral arms in the same place. There probably still would be spiral arms, but they would be in different locations and doing different things. So we don't think dark matter plays any direct role in star formation, which is part of why it is dark. It's hard to see. If it were playing a direct role, we would have found out about it sooner.
So thank you for making some complex physics sound pretty understandable. So I've read about this, I've heard about this, but I'd like your take on a short description of what actually was the Big Bang and why did it happen?
All right, so I'm going to start with, this is not my field. I did study it as an undergraduate, but this is what you're asking about is fundamental physics, not star formation, and interestingly, not really astronomy. The Big Bang is something we infer from looking at the cosmic microwave background. Okay, so all the caveats out of the way, I have no idea. I try to study this myself but I'm sort of studying it as much as an amateur as anyone else, in that the physics involved, we don't even have theories for. All we can say is that because we can see the cosmic microwave background today, we know there was some event that homogenized, that made the universe the same everywhere. And we have very, very good measurements of that. But